of these transport derivations using the exact same framework, but I think this one is maybe just a little bit more challenging to understand. So what I'm going to do is I'm going to derive Newton's law for viscosity. So I don't know exactly what your fluid mechanics background will be if you're someone sitting in this course. So this may or may not have been something that you've seen before in an undergraduate or graduate fluid mechanics course. But there's this concept that if I take adjacent sheets of fluid and sort of brush them by one another, that there'll be a restoring force in the form of a shear stress that develops. So like in a fluid mechanics course, the way you would write this is that there's a shear stress that develops on a particular element. So like, for example, on our little patch here that's sitting in here, if, let's say, one of these sheets is being pulled at some speed, Vy plus delta Vy, and the other one is, moving at some other speed. So essentially, like, if the adjacent fluids are moving at different speeds, there'll be a shear stress that develops, and that shear stress develops because there's a net exchange of momentum at this central interface. The same way that there's a net exchange of heat flux across that interface, or there's a net exchange of molecules across that interface if there's a difference in the number density, for example. So I'll write that as a shear stress, so a force per unit area that develops on the central plane in response to a gradient in the horizontal velocities. And so our job, or the goal of this exercise, is to figure out how big is that restoring force, this thing called the viscosity. So that's a Greek symbol mu. My Greek symbols are not so good. Okay, but actually the entire procedure works exactly the same way. So like, how would you calculate the shear stress? Okay, so it's a force per unit area. What is force? Force builds up in response to the rate of change of momentum. So what is the rate of change of momentum across that interface? So the rate of change of momentum, which is so per unit area anyway, the rate of change of momentum per unit area, or the force, would have to be in response to exchange of momentum. So what is the momentum density of the top or bottom layer? Well, that's the number density of molecules times their average speed. And then that would be evaluated at a particular layer, for example. So that would be at so that's the momentum density of each layer, and then how quickly they exchange it is basically this factor Vz. And then I guess we have to account again for the fact that only half of that momentum density goes in one particular direction, half of it goes the other direction. And if it's coming from the bottom, that would give a plus sign, and if it comes from the top, that would give a minus sign. From there, everything is the same. Basically, as soon as this statement, by the way, so let's just go back through this one more time. So this is the momentum density, right? So m times v is the momentum of an atom. To get the momentum density, you would have to multiply by the number density of atoms. So this will give the momentum per meter, essentially per meter cubed, and then you multiply that by something with units meters per second. So that's the momentum exchanged per meter squared per second across this element. And so this is the positive portion of that, and this is the net. This is what comes through the other end, subtracting from that. I can expand all that as a Taylor expansion, and we'll get something similar to what we've had in the other cases. So we'll get Vz times Lz times the derivative with respect to z of the stuff inside. We'll need to do a directional average. Doing the directional average, basically, you know, if I do the average, if I average everything, it'll just bring down a factor of 1/3 VL times that derivative. And then that derivative can be expanded. I guess typically when you do this, you assume that the number density of molecules is not changing significantly compared to the velocity. Like that shear is supposed to be a lot bigger. And so in that case, you get eta times m times dv y dz. And then you identify, let's see, is there a minus sign somewhere? I think I might need to be a little bit careful in this case with the minus sign. There should not be a minus sign in this case, but I need to think a little bit carefully about why that is. The force per unit area. I think it has something to do with the fact that I need to think about the top and the bottom portion of this element, because in one case the force is acting on the bottom and the other one's on the top. I'm going to just, you know, because I haven't really thought about that this carefully, let's take the sign out here with a grain of salt right now. I haven't really thought about why that sign changes, but anyway, sorry, let's not go into it. But anyway, this factor that sits up here can basically be identified as the viscosity, right? And so in that case, basically you can trace all this stuff back. And if you want to trace it back a little bit further and figure out the temperature dependence of viscosity and so on and so forth, what you need to do is basically replace this with 8 over pi times kBt over m, and replace this with, you know, 1 over eta times 1 over eta times the scattering cross-section. And again, you'll see that the so one of the key features here that I'd like to point out is that the number density actually cancels. So there's a number density here, but then there's a number density here, and so it turns out that, you know, viscosity, I'll just write a sort of scales as, when you're doing the scaling, it turns out that it scales as temperature to the half power and with mass to the half power, but it does have the scattering cross section here. So the scattering cross section and the mass tend to kind of cancel each other because the mass and the scattering cross section kind of scale in the same way. And so it's a much weaker function of mass than other things, but the temperature dependence of viscosity is absolutely correct, and the fact that there is no pressure dependence on viscosity is also correct and verified by experiments. So like those are some key points that you know. So basically, mu does not depend on pressure is a key point here. But anyway, but if you put all that together, basically you can calculate the viscosity of a gas, at least an ideal gas, based on this simple argument as well. And so we'll do all of these things again in the context of Boltzmann transport theory later, a little bit more advanced treatment. But you know, this is basically a cheap and easy way to get to these kind of scaling laws.